So in fact, what will be happening that from here, let's say this will be the source of our voltage, and from this point to the short circuit current point, all these elements of our network will be constituting a very small impedance, and this impedance will be responsible of limiting the current. And this current will be, of course, it is a very small impedance, and the current will be a very high current, as we have said. So for each element of this network, we will be giving it as equivalent circuit, an equivalent circuit for the medium voltage network. Of course, it will be a real part, which is a real resistance with an impedance. For the transformer also, for the conductor right here, for the main circuit breaker, and for any circuit breaker, for the bus bar, and so on. So all these elements will be written in a form wherever we will have a resistance and an impedance, and then at the end we'll be calculating the total impedance of our circuit. So to do that, we'll start with this part, figure G34. So figure G34, it will give us what is here RA and XA, which are the equivalent circuit of the medium voltage upstream network. So the upstream network, it is this part right here. So in order to understand that, so we have something common, that the manufacturer, or let's say EDL, will give us the power, the short circuit power of our network. So even it is 250 megavolt amperes or 500 megavolt amperes, and of course in Lebanon it is always 420 volts. And according to the short circuit power of this medium voltage network, I can indicate RA and XA. So let's say if I have a 250 megavolt ampere network, it will be 0.07 RA in milliohm, and XA will be 0.7 milliohms. So of course for the transformer also we'll have an equivalent XT, RT and XT that we can see here in this table. So what we'll be looking at the transformer, at the rated power of the transformer and kVA, and then we'll look at the USC, at the percentage of USC, which is on the nameplate of the transformer. We will see this later in details in the electric machines course. So according to USC, if it is 4% or 6%, and according to the rated power of the transformer, we'll get RTR and XTR. So for the moment, we'll be forgetting ZTR. And of course, we have two types of transformers, which are all immersed and cast resign. So all immersed, so it means that we have oil inside our transformer. Oil will be used to cool the transformer. And cast resign, it means that we have nothing inside our, of course, we have the coolant inside our transformer is not oil. So in fact, it is air. It is by natural convection of air that will be having the cooling inside our transformer. And of course, this is a note for you. So whenever I have indoor transformers, I'll be using a cast resign transformer or oil-free transformer. However, whenever I'm working, let's say in any place other than that, I can use all immersed transformer. So this is figure G35. So according to the power rating of the transformer and to the percentage of USC, I will be choosing RTR and XTR. Now for any network, I will be having some circuit breakers. So for any circuit breaker, the resistance of the circuit breaker, so the value of R will always be equal to 0. However, the reactance value is equal to 0.15 milliohms. For the bus bar, it is the same, so the resistance of the bus bar is negligible, is equal to 0. However, the bus bar, so it will be conducting power or electricity from one point to another point, and we will consider that we will be having 0.15 milliohm per meter as an impedance. For circuit conductors, so for each circuit conductor, we will see what is the type of this conductor. It is a resistance, it's a copper or aluminum. So we'll be calculating the resistance is equal to 22.5 milliohm per millimeter square per meter for a copper, and it is 36 milliohm millimeter square per meter for aluminum. So what we'll be doing, we will always be dividing per the cross-section area and multiplying times the length of the conductor in order to get the real value of the resistance and the real value of the inductance.